We discussed question 10 of A-Level Pure Mathematics 3, paper 3, in May or June of year 2020. We are given a complex number u equals 3i over a plus 2i, where a is real. And for part 1, we need to express u in the Cartesian form x plus iy. That would be the simplest form of a complex number. U is given by 3i over a plus 2i. To write it in the simplest form of a complex number, the denominator has to be real. And in order to make the denominator real, we must multiply by its conjugate, a minus 2i. We do the same for the numerator. For the numerator, we have 3ai minus 6i squared. And for the denominator, that is a difference of squares. So we have a squared minus the square of 2i. We know that I squared is negative 1 for complex number. So this I squared is negative 1. Negative 6, negative 1 gives us a 6. So we can write this as 6 plus 3ai. In the denominator, we have a squared minus 4i squared. Since I squared is negative 1, the denominator is a squared plus 4. In the form of x plus iy, so we can write this as 6 over a squared plus 4 plus 3a over a squared plus 4i. Second part, we need to find the exact value of a for which the argument of the conjugate of u is pi over 3. U is 6 over a squared plus 4 plus 3a over a squared plus 4i. The conjugate of u is just u, where this positive sign is changed to a negative. So the conjugate of u is 6 over a squared plus 4 minus 3a over a squared plus 4i. The argument of the conjugate of u is pi over 3. The argument of a complex number is the arctangent of the imaginary part over the real part. The imaginary part is negative 3a over a squared plus 4. And this is divided by the real part, which is 6 over a squared plus 4. That is pi over 3. The denominators are the same. We can actually cancel this to be a 1, so that the arctangent of negative a over 2 is pi over 3, or negative a over 2 is tangent pi over 3. Tangent pi over 3 is square root of 3. We have negative a over 2 equals square root of 3, so that a is negative 2 square root of 3. Part B, we need to sketch and shade the region satisfying the two given inequalities. The first inequality is the modulus of z minus 2i less than or equals to the modulus of z minus 1 minus I. That is actually the region above or below the line that is a perpendicular bisector to the point 2i and 1 plus I. In order to find the perpendicular bisector, we set the modulus of z minus 2i equals the modulus of z minus 1 minus I. Letting z equals x plus iy, we have modulus of x plus iy minus 2i equals the modulus of the modulus of x plus iy minus 1 minus I. You can group together the imaginary part. We have x plus I, y minus 2, and we have the modulus of x minus 1 plus I, y minus 1. The modulus of a complex number is the positive square root of the sum of squares of the real and the imaginary part. We have square root of x minus 1 squared and y minus 1 squared. Since we have square root on both sides, we can square both sides and we are just left with the expression under the radical, which we can expand. On the left, we have x squared plus y squared minus 4y plus 4. On the right, we have x squared minus 2x plus 1 plus y squared minus 2y plus 1. Can cancel off the x squared and the y squared so that we are left with 4y plus 4 on the left. On the right, we have negative 2x minus 2y plus 2. Rearranging, negative 4y plus 2y equals negative 2x plus 2 minus 4. Negative 2y is negative 2x minus 2. We can divide throughout by negative 2. Y is x plus 1. Then the perpendicular bisector of 2i and 1 plus I has the equation y equals x plus 1. On the Argand diagram, the horizontal axis represents the real part of the complex number, and the vertical axis represents the imaginary part of the complex number. We have the point 2i and the point 1 plus I. So this line y equals x plus 1 is a perpendicular bisector of this line segment. Y equals x plus 1, the y-intercept is 1 and then the slope is 1. So this line is just a straight line passing through those 2 points. And since the distance between the complex number is closer to 2i than 1 plus I, we are looking at the region above this line here, the perpendicular bisector. The second part of the inequality, the second inequality given to us, is the modulus of z minus 2 minus I less than or equals 2. So we are looking at the region. We can write this as z minus 2 plus I less than or equals 2. We are looking at the region inside the circle. This gives us a circle where the center is 2 plus I and the radius is 2. So we have 2 plus I as the center here, and the radius is 2. So we need to draw a circle with a radius of 2 and the center of 2 plus I. So that gives us a circle with radius 2 and center 2 plus I. We need to shade the region inside the circle and above this line. That is the only region that we have that is inside the circle and above the line y equals x plus 1. So that gives us the solution for part 1. For part 2, we need to calculate the least value of the argument of z. For points in this region, you have any points on this region. The argument is the angle between the real axis and the line from the origin to any point in this region. Let's just consider any points here. So from the origin to any point, we are looking at this angle. And we need to find the smallest angle. The smallest angle that we have is from the origin to that point of intersection between the line and the circle. That is the smallest angle that we could find. So this will give us the smallest angle. Any points else, any other points in this region will give us a bigger angle. So we need to find this. This is the argument of z that we need to find. We need to find the points here, the real and the imaginary part of this point. This is the point of intersection between the circle. So we only consider the circle where you have the modulus of z minus 2 minus I equals 2. And now we let z to be x plus iy. So the modulus of x plus iy minus 2 minus I equals 2. We have the modulus of x minus 2. And the imaginary part is y minus 1 equals 2. The modulus is the positive square root of the sum of squares of the real and the imaginary part. Squaring both sides, x minus 2 squared plus y minus 1 squared equals 4. Now we are going to, because we are finding the points of intersection, so we can replace this y with x plus 1, which is the equation here. So when y is replaced with x plus 1, this part becomes x squared. We have x squared here, and then expanding the square of x minus 2, we have x squared minus 4x plus 4, that equals 4. So that 2x squared minus 4x is 0. And we can factor 2x, and we have x minus 2 equals 0. X is either 0 or x equals 2. From the diagram, clearly x is 2. We can substitute x equals 2 into the equation, y equals x plus 1, and we have a y value of 3. Then this is the complex number, which can be written as 2 plus 3i here. That is the complex number that we look at. Then this value of the argument of z, we are looking at the argument of 2 plus 3i. That is the arctangent of 3 over 2. And in radian, that is 0.3. 98.